Mole fraction X is a unit of concentration. It can measure any unit of concentration. Since it's a fraction, it is part to whole. In this unit, it will measure the concentration of mole and partial pressure. The symbol X is the symbol for mole fraction. It is equal to the partial mole over the total mole, which is also equal to the partial pressure over the total pressure. Since mole fraction is a fraction, it is unitless, which means there are no units. For example, if the partial pressure is in torrs, then the total pressure is also in torrs, so the units cancel out. In this first example, we have 3-liter sample at 15 degrees Celsius, contains 0.030 moles of N2 and 0.002 moles of argon. If the total pressure is 0.52 atm, what is the partial pressure of each gas? So there are 2 ways to solve for this. If you identify all the variables, you'll notice there is one variable for each. So the gas law we will be using here is the ideal gas law. We could use the ideal gas law, or we could use mole fraction. We have 2 gases here, nitrogen and argon. N of N2 over the total moles is equal to the partial pressure of N2 over the total pressure. We know the total moles because N total has to equal to N of N2 plus N of argon. So this is equal to 0.030 moles of N2 plus 0.0020 moles of argon. If you add that, you will get 0.032 moles. And the sig figs are correct because if I line up the decimal, this is the least precise position, so it replaces after the decimal. So for N2, we know the moles of N2. The moles of N2 is 0.030 moles divided by the total moles, which is 0.032 moles. This is equal to the partial pressure of N2 over the total pressure, which was given as 0.52 atm. So if you solve for the math, N2 is equal to 0.4875. To do sig figs, the top number here, 0.030, has 2 sig figs. Decimal significant digit in front, the 0 after the 3 is significant, but the 0 in front is not significant. It's a placeholder because there's no significant digit in front. 0.032, we already said there is 2 sig figs. 0.032 has 2 sig figs because this 0 right here is a placeholder. There's a decimal but no significant digit in front. And 0.52 atm has 2, so my final answer needs 2. Starting from the left, the first non-zero digit is 4, 1, 2, 1 to the right. So this becomes 0.49 atm. To find the pressure of argon, we could plug it in. 0.0020 moles of argon divided by the total moles, which is 0.032 moles, is equal to P of argon over the total pressure, which is 0.52 atm. And you can solve for PAR. The other way we could do this, which is a lot easier and faster, is the P total has to equal to the pressure of nitrogen plus the pressure of argon. Since we know the total pressure is 0.52 and we know the pressure of N2 is 0.49 atm, if we subtract, we could find the pressure of argon. So pressure of argon is going to equal to 0.0325 atm. With correct sig figs, we have 0.52 and then we have 0.49, so we're going to have it 2 places after the decimal, so 1, 2. So my answer is going to be 0.03 atm. So you could solve it with PV equals nRT. It just takes a lot longer. If you do the mole ratio and there's only 2 gases, if you know the total pressure If you solve for one, you could subtract the other, or you could replug it into the equation. Pause the video, try this example on your own, and then check your answer. So on this one, first thing we're going to do is identify the variables. We know T is 315 kelvins. If you're having trouble determining which variables go with which number, check the units. The units will help. Kelvin is a unit for temperature. 6.9 liter is the unit for volume, so it's 6.9. It contains H2 and helium, so we already know this is a Dalton's partial pressure because there is more than one gas or a mixture of gas. The total pressure, P, is equal to 900 torrs. We know the moles of H2. What is the partial pressure of HE? So in order to find the partial pressure of HE, we need to find the moles of HE. Since the moles of HE is not given and the pressures are not given except for the total pressure, I need to use PV equals nRT to find the total moles. Because since there is only one P, one V, one T, we know the equation we need to use is PV equals nRT, and we're going to use this formula to find the total moles. Once we find the total moles, we could use mole fraction to solve for the pressures. So the pressure is 900 torr. Since we're using ideal gas law, it needs to be converted into ATM. So diagonal units, torrs. There's 760 in 1 ATM. The volume does not need to be converted because it's already in liters. This is equal to the N total because the 900 was P total times the gas constant times the temperature, which is 315 Kelvin, so it does not need to be converted. So you're going to multiply the left side and then divide by the right side. So N total is equal to 0.3161 moles. At this point, if you want to do sig figs, you can. I usually wait till the end and keep track of my sig figs. Next, I know my partial pressure we're looking for is helium. This is over the total pressure. This is equal to the moles of helium. To find the partial pressure of helium, we need to use the moles of helium. To find the total moles, we need to use the total pressure. To find the partial pressure of hydrogen, we need to use the moles of hydrogen. This is over the total moles. We are looking for the partial pressure of helium. We don't know. The total pressure is given in torrs, 900 torrs. We do not have to convert unless it asks. We converted in PV equals nRT because the gas constant is in ATM. We don't know the total moles of HE, but we could find it because total moles is equal to the moles of hydrogen plus the moles of HE. So that's going to be 0.3161 moles equal to 0.034 moles hydrogen plus the moles of helium. So the moles of helium is equal to 0.2821 moles of helium. So the moles of helium, 0.2821 moles over the total moles, which is 0.3161 moles. Do the math by cross multiplying or multiplying each side by 900, and you solve that P helium is equal to 803.20. Now we're going to go back and do sig figs. When I calculated the PV equals nRT, there was a decimal after the 900, so there is 3 sig figs for pressure because decimal significant digit, the zeros are significant. The volume had 2, the temperature had 3. This is a conversion factor, doesn't count. This is a conversion factor, doesn't count. Since we're multiplying and dividing, the least amount, so you need 2. 1, 2, I look it to the right. This is technically 0.32 moles, so there's 2 sig figs. After I do that, I need to line up, so 0.32, and we're going to minus 0.034, Last significant digit in the total moles is the 2. The last significant digit, hydrogen, is the 4. Least precise is here, the 100th. So that means this is going to be rounded to the 8th. So this one is going to have 2 sig figs. So this number has 2 sig figs. This number has 2 sig figs. This one has 3. So my final answer has 2. 1, 2. Look 1 to the right. So this is going to be 800. If I leave it as an 800, there is 1 sig fig. So I'm going to round here. So we need to write it in scientific notation to the second and units of torrs. Pause the video, try this problem on your own, and then check your answer. So we have a mixture of gas, neon, hydrogen, and nitrogen in a 3.0 container at 25 degrees. Determine the mass of each gas. Partial pressure of Ne is 3, partial pressure of hydrogen is 1.3, and nitrogen is 2.5. We could find the total moles using the ideal gas law. We have a volume, which is 3.0 liters, temperature, which is 25 degrees Celsius. We have pressures. To find partial pressure, we need to find the total moles. To find the total moles, we need the total pressure. We could find the total pressure because we have the partial pressure of each, and this is a mixture of gas. So total pressure is going to be pressure of neon plus the pressure of hydrogen plus the pressure of nitrogen. So this is 3.0 atm plus 1.3 atm plus 2.5 atm, which equals to 6.8 atm. And the sig figs are correct. Last significant digit for 3.0 is the 0, which is at the 10th place. Same thing for 1.3 is at the 10th place, and the last significant digit for 2.5 is at the 10th place. So the total pressure is 6.8 atm. Now we're going to plug it into PV equals nRT because there's one variable of each, and we're going to find the total moles because we have the total pressure. If you want to use PV equals nRT to find the moles, you need to use the partial pressure of each one. To find the moles of Ne, you need to use the partial pressure of Ne and not the total pressure. To find the moles of hydrogen, you need to use the partial pressure of hydrogen. And to find the moles of nitrogen, use the partial pressure of nitrogen. So plugging into PV equals nRT, 6.8 atm. Does not need to be converted because it's already in atm. Volume is already in liter, does not need to be converted. This is equal to N total because we're using the total pressure times the gas constant times the temperature, which needs to be converted to kelvins by adding 273. So N total equals to 0.8342 moles. So if we do sig figs here, there are 2 sig figs for the volume, decimal significant digit. For the temperature is 25 and 273, so we're going to line it up here. So there's going to be 3, and the pressure already has 2, so that means the number of moles is going to have 2. 1, 2, I look 1 to the right. So this is going to be 0.083 moles. At this point, you could plug it into PV equals nRT. I'm going to use mole fraction. So mole fraction generic formula is PA over P total, NA over N total. So if we're looking for the first one, which is neon, this is going to be the partial pressure of neon over the total pressure equal to the moles of neon over the total moles. So the partial pressure of neon was given as 3.0 atm. The total pressure we calculated as 6.8 atm. This is equal to the moles of neon over the total moles, which we calculated as 0.83 moles. If you solve the math, the moles of neon become 0.368 moles of neon. But we do not want the moles, we want molar mass. So we need to do stoichiometry. Moles of neon, molar mass here. Diagonal units have to cancel out. 1 mole is equal to approximately 20.18 grams of neon. So multiply the top, you get 7.4 grams of neon. And there's 2 sig figs. This is up here, there was 2. You repeat the same thing for hydrogen. Pressure of hydrogen was given as 1.3 atm. Total pressure is still 6.8 atm. This is equal to the moles of hydrogen over the total, which is 0.83 moles. So the moles of hydrogen, once calculated, is 0.159 moles of hydrogen. The mass of this, so we need to continue on, 0.15 moles of hydrogen. I'm going to do dimensional analysis, so this is going to be moles of hydrogen. 1 mole, which is 2.02 grams of hydrogen. This is equal to 0.32 grams hydrogen. So the last one, we could plug it into the equation again, or we know that the total moles is equal to the moles of neon plus the moles of hydrogen plus the moles of nitrogen. So if I plug this in, this is going to be 0.83 moles is equal to moles of nitrogen, which is 0.368 moles, plus hydrogen, which is 0.159 moles, plus moles of nitrogen. So the moles of nitrogen is approximately 0.307 moles of nitrogen. We don't want the moles, we want the mass, so we need to do molar mass. Nitrogen, diagonal is 1 mole of nitrogen because diagonal units have to cancel out. There's 28.02 grams of nitrogen, and so this is equal to 8.6 grams of nitrogen. So if you notice, there's more than one way to solve for this. You could use PV equals nRT. It just takes a lot longer to set up. However, sometimes you need to use PV equals nRT to get the total pressure or the total moles. Once you have the total pressure or the total moles, you could use mole fraction. It's a lot faster.